Okay, previously we talked a little bit about the mechanisms by which you could get two fluids to be able to invade pore space of porous media. And what we had done was we had looked at models that included idealizing the system basically as a series of capillary tubes. So what I want to do today is to recap a little bit about what we did last time, and then you'll recall that what we talked about last time was the behavior by which we could get fluid into a bunch of capillaries and the ramifications of that. So today what we'll try and do is take it the next step and give some practical application of that, if this pen works, okay, which it does. And we'll talk about what I've referred to as capillary pressure versus saturation curves, which are really what are the standard method of looking at porous media and the invasion by other fluids. We'll talk about why the behavior of getting one fluid in and another fluid out of a porous medium has a hysteresis to it. It matters whether how you're changing saturation of water, whether you're increasing the saturation of water or decreasing the saturation of water as to which path you take. And then the implication of that is how deep can these NAPLs go, which is kind of epitomized in our couple of figures of D NAPLs and L NAPLs, and exactly what the profiles look in terms of the distribution in the subsurface, and then figure out exactly how to evaluate these capillary pressure versus saturation curves. So that's kind of the plan for today. So in terms of recapitulating what we talked about last time. So the basic idea last time was that we thought that we could take a porous medium and we could idealize this porous medium in terms of this pore throat size. Let me increase the size of this. And so this pore throat we could actually represent as a capillary tube, or a series of capillary tubes, a bundle of capillary tubes as is often referred. And our simplest way of looking at that was to basically turn these tubes on end, dip them in water, and as a result of that we ended up with some height rise of fluid within there. If this was a wetting fluid, it would rise along the glass because it likes glass, it's hydrophilic, and it rises up to some height. And based on that height, we could develop a couple of relationships. We actually developed two, but the most important one was to note that the height rise was equal to something like 4 times the interfacial tension divided by the diameter of the individual pipe. And so that was useful because it told us something about the height rise. It's directly proportional to interfacial tension. The higher the interfacial tension, the higher the rise. And the smaller the diameter pipe, also the higher the rise. And we kind of know that intuitively. And so this is the same behavior that you'd expect to have in these horizontal pipes. But it's easier to define this as a term which represents the capillary pressure. And the capillary pressure we defined as being, by convention, the difference between the pressure in the non-wetting fluid relative to the fluid pressure in the wetting fluid. And that difference is measured adjacent to each other, where the pressure in the wetting fluid, in this case, which would be water, and the pressure in the non-wetting fluid, in this case, would be air. The difference between those is really defined by the curvature of this surface. And this curvature of the surface is really the force that you're having to apply to pull this fluid up beyond the level it would like to be at if it sits in the bottom here. And we could define this also as the height rise multiplied by the unit weight of the fluid, right? The product of these two is just a pressure. And so if we use this, I guess I didn't do this, right? This is incorrect, right? This has a unit weight in it. Then the capillary pressure is equal to 4 times the interfacial tension divided by the diameter and the unit weight of water and the unit weight of water. both cancel out. And so this also has the same relationship, and that is that the height rise you get, or the pressure differential between these two, increases as you increase the interfacial tension. As it likes the surface of the glass more, it will increase the magnitude of the pressure differential because the curvature of this will become more extreme. And as you decrease the diameter of this capillary tube, it will also rise higher, and that's caused by the fact that you have a higher pressure pulling this flow up also. So that's basically the important characteristic that we got out of this. And so, without getting too involved in this, since we know that the capillary pressure here is proportional to interfacial tension and inversely proportional to diameter, then the ramifications of this are that if you look at trying to drive fluids along two pipes, then the smaller of the pipes will be more resistant to moving, not the fact that it moves at a lower velocity, but the fact that it can't move at all. It can't physically get into the pipe. It can't invade the pipe. But the larger diameter pipe, it'll be happy as a lark, and it'll just move along to be able to get to wherever it needs to at whatever rate it's able to flow at. And so there's a fundamental difference in porous media as to how they can invade in the small pore spaces versus the large pore spaces. And so you can imagine it makes a difference as to whether these pipes are arranged as a bundle in parallel, as they are here, in which case you'll always get breakthrough occurring through the system. If you, I guess perhaps I can do this. I wonder if it'll work if I can do this. Oh, I can. Wow. Is that the right orientation? Yeah, right. So if you have this invading under gravity in this big pore space, it'll just happily go down here. But if you have an arrangement of large pipes and small pipes in series, then it'll get very easily into the largest pipe, but it won't be able to get beyond this, and it'll stop. And so that's the reason why when we go back to look at the cases we looked at before, which was this figure of invasion of a porous medium, this figure here. And that is that as you look at this NAPL, which is invading water in this glass bead pack, it's chosen a certain route. It's gone this route that's been through here, and it's chosen not to, for instance, go here. It's stopped at this pore throat. And so the question is, why is that? Well, the reason is that presumably the pore throats here are smaller than the pore throats here in some way, and it's chosen to go in this direction. It's got an easy pathway through this, and once it's wetted this tongue that travels through this portion of the pore space, it doesn't have to reassert itself to re-wet it. And so all the fluid that flows here flows just naturally. The only effects of interfacial tension are going to be right on this boundary, and if it's not moving this boundary, then that's in some kind of equilibrium, and the fluid is happy just keeping on going down this interior pathway and moving down deeper into the subsurface. So that's the reason why we get these fingers develop in porous media. And the consequence of that is that if you look at the saturations that you'd see in porous media, both in the saturated zone and also in the vadose zone, they're very patchy. You'll have a plug of NAPL sitting here, you'll have water sitting next to it, you'll go along a couple of meters and you'll see another plug of NAPL. And so that's one of the major challenges, is being able to work out exactly where the distributions of these spotty saturations are. Okay, so that's one implication. So the other implication of this is that we can also use the same kind of analysis to be able to look at flow in other features which are different from porous media. And one important behavior is for looking at flow in fractures. So if you imagine spilling something onto one of these 55-gallon drums. If you imagine spilling some liquid into the ground, and if you have porous medium, it will do what we talked about. It'll find some pathway down through that, and depending on how open that pathway is, it will be able to flow or not. But if you imagine that ground having a whole series of fractures in it, and these fractures might be more open, you could imagine, than the porous medium, then in preference, if these fractures have a larger equivalent diameter to the porous media that surrounds them, then clearly it will go on the fractures. So we can use the same kind of analysis that we've done before to be able to look at how flow would occur on fractures. Simple idealization is thinking of this. So you take the analog to a capillary tube is to two parallel plates of glass that you stick into water. They're separated by a small separation, maybe a millimeter, something of that order, or less than a millimeter. And the plates of glass have some length into the page, if you like. And you can do the same analysis. You'd think that the water would rise in there to some height. It's pulled up by the interfacial forces which act at the contact between the water and the plate, which runs kind of, well, along here, right? And we can do the same analysis. We know it's atmospheric pressure here. It's simply connected as we go here, so at the same elevation, this has to be atmospheric as well. If that's the case, we can cut this off here, and we can draw a free body diagram that looks something like this. And this is the aperture. This is length into the page W. This is this same height H sub C that we've talked about before. And we can just do a force balance on the weight of this water relative to the forces that are applied along this portion here. This is some force F. And we can look at resolving those in the vertical direction. So what do we have acting downwards? We have the volume of this is equal to the width of the fracture, the length into the page, and the height of the water. So this is basically the volume of this plug of water, which is just, we're picking up. The unit weight of this is gamma W. So this together is the weight of this whole system as a force, and acting downwards. And so acting upwards, we have a force which is equal to this F, which is going to be equal to the surface tension times the surface tension times the length over which it acts. There's one on, so this is actually the magnitude of the force. There's one on each side, so there's one here and there's one here, right? There's this, and there's this. So there's two of them. So this is the total force. But we want the component which acts in the vertical direction. So rather than take the value of F, we want F cosine theta, where this angle here is theta, the contact angle. So this overall is the force magnitude in this term here. We have two of them, and the component that acts vertically is going to be the cosine of the angle. And it's probably a relatively small angle, and it's close to 0, and therefore the cosine of 0 is close to 1. So if you equate this, you end up with a very similar relationship for this height rise, just as before. The only difference is that this is this is an aperture rather than diameter. And if we take the capillary pressure, and we realize that the capillary pressure is just equal to this height rise times the unit weight of the fluid, just as before, then we have a capillary pressure, entry pressure into the system, that is this magnitude here. And so we can define the capillary pressure that will actually force fluid to move between these parallel plates as an analog to a fracture as being equal to this. And so this is directly analogous, I think, to the magnitude we had before, which was this entry pressure, being able to move the fluid along into the pore space, where we're looking at the diameter of the pore rather than the aperture of fracture. So those are important relationships for us. And our interest in that is being able to say something, for instance, about how fluids invade pore spaces, where clearly there's not just one state, if you like, as is suggested by these bundles of capillaries. All the work that we've done here has basically said that there's a capillary pressure which is given by an equivalent diameter of the pore throat diameter and the fluid property in terms of the interfacial tension. So that gives one value of the capillary pressure. But the reality is that a porous medium will have a couple of differences from that. The first is that the pore space will have a whole bunch of different pores in it, which will have different diameters. So we need to think of it as maybe a bundle of capillaries with different diameters. And we talked about that in terms of this arrangement that we had before as big capillaries and small capillaries either in parallel or in series. So that's one issue, is that the pore throat diameters will be very different to each other. And the other behavior that's different for us is that the saturations that we have of water and oil in the system can vary in some degree. And so there's a variable state, not just a single behavior that we would have in these systems, that depends on something else. And so we need to be able to use what we've gathered already to be able to understand something about this, how the saturations will change as a function of the capillary pressures that we apply to these systems. And so that's our interest in this. So that kind of brings us to what I wanted to talk about today. And we'll come back to this picture later. So here's the deal. We've described how we can get capillary pressures as a function of the diameters of these tubes. Actually, perhaps it's worthwhile looking at this now. So this is where we are. What we want to do is now we want to be able to say something not only about whether this can invade the porous medium, but we want to be able to say something about what the distributions of the different fluids will be somewhere in portions of this plume once it's reached the steady behavior, or before it reaches the steady behavior. We'll have some behavior, in this chimney up here, where it's gone through the unsaturated zone. It's left a smear, as we said, of NAPL, which is shown here is this red color. And also there'll be this lens, which is nearly fully saturated with the NAPL, which will be perhaps have a higher saturation of the NAPL, but it'll differ from this area in the amount of NAPL that's there, in relatively the proportion of it, but not in any other significant way. So if you look at a snapshot of what this would look like, it would look exactly like that figure that we went through before, and that is that we'd have grains, which are these brown areas. We would have water in the unsaturated zone, which fills up some of the pore space. We'd have air in some of the pore space. This is the partially saturated zone. And as you add NAPL to this, it will be accepted, if you like, into some of the pore space and displace the air and or the water as it invades this component. So what we'd like to be able to say something about this is what is the proportion of NAPL and water and air that we might have at any particular location, either in this chimney, this column, or within this much higher saturation of NAPL zone here at the bottom, where it's going to pool on top of the water table and then dissolve in the groundwater and be carried away. And so that's kind of our next task, is how do we describe the saturation changes, and how would we expect them to change with depth as we go down through this. Okay. So we do that by something that's called a capillary pressure versus saturation curve. And maybe the best way to describe this is to go right to the end of what we're going to talk about in this and talk about the experiment that we might do to do this. So it's a little bit out of sequence, but it may be worthwhile doing that. So this is a picture of the apparatus you might use. It's called a Welch apparatus, and it is relatively straightforward in that it is basically a beaker, which is this component here. A beaker that has a tube coming out of the bottom of it, and in this beaker sits a frit, just a porous piece of porous metal. And on that frit you place your core. So this is a core that you've taken out of the ground, and what you surround this core with is an oil. So initially this core is saturated with water, or a brine, since this is kind of taken from the case of a oil field where the waters are usually brines rather than just sweet waters. And so it's initially saturated with water when you put it in here. You fill around it with oil, and you put a close on this beaker with some kind of pressure holding stopper. And below this you have the same water that's present within this sample. So it's either a brine or it's just a water. And through this frit, the water in the porous medium is able to communicate with this, but the frit excludes it from the portion which is outside the, it doesn't allow this oil to directly squeeze into this. And so what you do is you increase the fluid pressure in the oil just by applying a nitrogen pressure or an oil pressure for that matter, so that the pressure in this oil surrounding the water infiltrated core increases by some step amount. And if the step amount of the increase in pressure in this oil is large enough relative to the pressure in the water in this core, which won't change, in other words the capillary pressure, so this is the pressure that starts off in here inside this core. And what you're going to do is you're going to increase the pressure in the non-wetting fluid, which is this fluid here. And if the difference between these pressures is big enough, then it will start to invade into the biggest pores that you have in the side of this core. If it's not big enough, it won't. And so you start off with a small increment and you see whether there's any invasion. And the only way that you can see if there's an invasion would be that if you get a non-wetting fluid going into here, then there's a change in volume of this, and some water has to be pushed out of this system. And so there's a change in the volume of the water in this pipe, and that will be recorded by this physically going up. So you can measure the change in volume if it goes up this height, and you know the diameter of the pipe. You can calculate, of course, the change in volume that's going into this pipe, and of course that has to have come from here. So what you can do is you can measure the change in volume. If you know the change in volume and you know the volume of the pore space, you can calculate the change in saturation, because we know that the saturation of water is equal to the volume of water over the volume of the voids. You can measure the volume of the voids, it's assumed in the course in some way. And so by knowing what the volume change of the water that's expelled, you have a change in volume of the water gives you the change in saturation, or you can get the absolute magnitudes as well. And so as a result of that, you'll know that the volume of water actually will be the negative, right? The saturation, if this amount increases, it means there's water coming out of this, and so the saturation of water would be going down, be decreasing. So don't worry about the sign, but that's exactly what would be going on. So what you can do is you can slowly increment the pressures that you apply here and measure the volume changes, which you can relate to the saturations, and you can basically attempt to make a relationship that links these two properties. And so that's the experiment that we would do to be able to define that. Okay, so let's go back to what we were trying to make the case for before. So that's essentially what we would do. So here's the idea. So you go in, you measure a, yeah, what I'm going to do, I can do it on here, I guess. So what you do is you go in, you apply this, if this here is capillary pressure, you apply small capillary pressure, which initially is 0. There's no difference between the pressure in the oil and the water, and you know that the saturation of this core has to be 1. Nothing's changed. You increase the pressure of the oil, and if it's not high enough pressure to be able to invade any of the pore space of the core and therefore squeeze water out of it into this U-tube, then you'd also have a no change in saturation. If you increase it again to some magnitude, it's not big enough to invade, or it's right at the verge of invading, then there'd be some very small change in saturation that you'd be able to measure. If you increase it some new amount, up to here, then what you'd find out is that it would go across horizontally to some point, and it would squeeze a certain amount of water out, and that amount of water you can measure. And if you measure that amount of water, you can plot this point relative to the pressure that you've added, and you have a single point here. You increase the fluid pressure again by some amount. It will invade the pore space. You can calculate what the magnitude of the change in saturation you get from that particular invasion is, and you get another point here. You increase the pressure again of the oil, it invades the pore space, and you end up defining another point. These pathways don't make any difference. You increase the pressure and it squeezes some fluid out slowly. You're interested in the equilibrium behavior, and you end up with this curve, which is, in terms of water saturation, 100% water, 0% water, and a capillary pressure, has defined a curve that looks basically like this. And that's purely as a result of being able to increment the fluid pressures and measure the saturation change you have in this sample. And so the idea is that you do this in the laboratory to get this curve, but of course this curve should also apply in the field if you're looking at knowing what the pressures are that you have in your unsaturated zone or within your aquifer or your reservoir. You should be able to, if you know the capillary pressure, you should be able to figure out exactly what the saturation is, and therefore you have some way of being able to know not necessarily what the topology of this in terms of where these things are, but you know on average the saturation of the NAPL is going to be some amount, and the saturation of water in the system is going to be some different amount, just for the two-phase system. So we're only looking at a two-phase system here, water and oil. So water, saturated sample starts out, and you start pushing oil into it to get up to this point. If now you back off with the capillary pressure, then you take a different pathway. So in other words, if you now from this point you reduce the capillary pressure by some amount, then you'll get a new saturation, which will be this point here. If you back off the capillary pressure again by some amount, you'll end up with a new saturation, which at this point is here. And so the bottom line is that you'll end up with a curve of two trajectories, I suppose. One is where it is pushing the oil into the system, and one where it is pushing, allowing the oil to come back out of the system and reinserting water. And so that's the basic deal. So you'll notice that this curve isn't defined in terms of capillary pressure. It has a number attached here. So let's look at these behave. So this is a typical capillary pressure versus saturation curve. This is water saturation. This is proportional to this capillary pressure that you apply. And if you had a variety of different reservoir rocks, these are just different sandstones, you'd end up with different curves because they have different characteristics. They'd have different pore throat distributions. So if you do it with one sandstone, you'd get a different response to the one you'd get from a different sandstone. And that's useful to know. But what you can do is you can use the great power of non-dimensional analysis, as again we've used in fluids classes, to be able to collapse all of these individual curves onto one curve. And we don't have to worry too much about the details of doing that, but basically this Leverett curve, which we have dealt with here, allows us to collapse all of these individual curves that we'd get onto a single curve, and where instead of plotting the behavior in terms of capillary pressure versus saturation, we merely go ahead and plot the magnitudes of the so-called J function. And so the J function is a proxy, if you like, for the capillary pressure. It's proportional to the capillary pressure, but it's multiplied by a number of characteristics for the porous medium and the fluid that we hope that we might know. And so these characteristics are three. The first is the form of the fluid that you push into the pore space, and that is that we want to know something about the interfacial characteristics of the fluid that is invading, the interfacial tension between the water and the oil in this particular case. We think that the permeability of the medium would make a difference, because the permeability, which is in units of length squared, should be in some way proportional to the diameter of the pore throats, or the grains, squared also. They're both the same units, And it turns out that if you have a high permeability is a high permeability because the capillary diameters are large. And if you have a small permeability, it's small because the capillary diameters or the pore diameters are small. And so permeability scales directly with the sizes of, sometimes you think of it as the grains, but really it's the pore throats that you have in the system. So the pore diameter is going to have something to do with it, and we use permeability as a proxy for that. And N is the porosity of the system. So these are the parameters that scale it. And so if you plot your graphs that you have here, instead of in terms of this capillary pressure that you have here, you plot them in terms of capillary pressure divided by the interfacial tension and multiplied by the permeability of the particular sandstone and the porosity of that sandstone, then the idea is that they all collapse onto a single line. They don't quite, but they have a relatively small range. And therefore you can use this single type curve to represent all rocks. It's basically the idea. So that's the idea here. And that's useful because then the ordinates of this, where this is 0.3, tell you something about the first point where you get invasion of any of this oil into the sample. And so if you know that invasion begins at this value of 0.3, and so this value of J is 0.3 when this occurs, then if you know what the fluids are that you're putting into the system, so you know the value of interfacial tension, if you know what the permeability of the aquifer is, which is something you can measure quite easily in the field. It's much more difficult to measure capillary pressures than it is to measure permeabilities, or you can estimate. And you can also measure the porosity of the material in the field. Then you have everything that you know to be able to calculate the pressure you have to apply to push the first amount of NAPL into the system. And the significance of this is that really when you look at these plots that we have for invasion, the pressure here is exact. When you invade this portion here, the capillary pressure that you have to apply to be able to invade this is exactly this capillary pressure that we've just talked about. And so this is the pressure at which you just begin to invade into the pore space ahead of some stop. And so you can use this curve to be able to say exactly when you would be able to invade and not. Ignore the rest of the stuff below this curve. So in other words, you're trying to push stuff into this pore space. If the capillary pressure that you're applying is less than the entry pressure that we've just calculated, P sub C from the Leverett plot, then it won't go in. You have to increase it at least to that level, and when you get to that level, it will just happily migrate into the system. So that's kind of the reason for talking about this capillary pressure versus saturation curve. So it's a very, very important curve. And these magnitudes that we have shown on this particular curve here, these actually are J-function magnitudes. And so this is actually the scatter of the values. So these aren't plotted as PCs. They're actually plotted as PCs, capillary pressures divided by interfacial tension and multiplied by this permeability over porosity term. And so they don't exactly form around this 0.3 mark as we saw before, but the scatter isn't too much, right? So this is 0.45, this is 0.1, and in the terms of the ranges of the uncertainties that we have in the systems that we're dealing with, uncertainty of 50% less and 50% more is trivial in terms of the uncertainties we have in groundwater systems. So it's an incredibly powerful method to be able to do that. Okay, so those are the Leverett curves. It's important for us to be able to define some different portions of this curve. It's probably easier for us to look at it in terms of just this characteristic curve that we have here. And so let me blow that up slightly. So what are the characteristics that we would think? So let's just say that this curve here is representative of every single porous medium that we have, because all these, the curves for any other porous medium have collapsed onto these two curves. So one that has this behavior here. So we're going to call this parameter here PC0. PC0 is the value at which you first get invasion of this oil into the pore structure. Almost at zero saturation of the NAPL. So this is 100% saturation of water. And so if you think about this along here, any value that you have here, so at this point here, if you think about it, will be a saturation of water and a saturation of the non-wetting fluid, right? So in this case, this will be about 10% saturated by the non-wetting fluid and about 90% saturated by water. They have to add up to 100% between them, right, for these two-phase systems. And so the idea is as you increase the capillary pressure, you invade. This curve is called the drainage curve. It's called the drainage curve because you're draining water out of the system. You're decreasing the saturation of water as you move in this direction. And water is draining out of the system. It has to go somewhere because you're invading it with NAPL. And as you go up here, you reach some limiting value. And you'll see that this doesn't go to the axis. It kind of asymptotes to the vertical, but there's always some amount that's left here. And we'll call that SW0. So SW0 is the irreducible saturation of water. And it's saying that once you've applied a really big pressure to be able to push this NAPL into the system, there's some small amount of water that's still left. And so no matter how much you try, ignore the fact that we have air here, no matter how much you try, you'll always end up with some water left in the system. And we've seen that, I guess, before. If you remember looking at the case where we had these funicular curves, right? This is the case here, so it's full of oil, but there's some small amount of water that is residual in this pendular saturation that we talked about. It's present as a monolayer of water around each of these grains, and it's also present as a ring of water that goes like a donut that is a period on one side of this grain and the other side of this grain, and it goes around the grain in a ring like a donut, a torus that goes around here. So we start off with lots of water in the system, we slowly put more oil in the system, and so we think the saturation would change like this. And so if you look at this curve here, if I would draw our capillary pressure versus saturation curve here for saturation of water of 0 and of 1, this is capillary pressure or J value, it doesn't matter. They'd be different units attached to these, and we have a curve that looks like this. Then this would be this point here would be C, this point here would be B, and this ultimate point here would be A. And so we can think what the saturations would look as you transit across this individual curve. So it gives us a picture. We know the magnitudes of the saturations from this curve. We don't know exactly how they'd be distributed, but typically, since we know the behaviors of wetting fluids, which are the water, and the non-wetting fluids, which is the oil, then we know how these would change from this so-called funicular saturation to pendular saturation. Or I guess the direction we're going from almost fully 100% water-filled to almost fully 100% oil-filled. But we never get 100% oil-filled because we never get across this threshold. Okay. So we know exactly what those would look like. So it's quite a powerful method that we have. So we define some anchor points of this curve. So this is the irreducible saturation of water. Always 3%, 5% of water left in the system, even when there's 95% oil. If we then drop down the pressure that we apply in the oil, then what we get is imbibition. So imbibition is imbibition of water. And what this means is that because the water is attracted to the surface of the grains in a water-wet system, it's hydrophilic, loves water, then the water spontaneously imbibes. So it just gets sucked back in. So as you drop the pressure, the water happily imbibes, and it comes along a curve. The curve is the same as the curve for the drainage curve for part of its way, but at some stage it bifurcates and it has this hysteretic form. And as you drop the pressure back down to the original zero pressure, you come to a magnitude here. And this magnitude says that now you've put oil into the system, you're left with some irreducible saturation of the wetting fluid. And this irreducible saturation, of the non-wetting fluid, this irreducible saturation of non-wetting fluid is what we would call S non-wetting 0. And in this particular case, it's about, it's not this 80% value, because that's the amount of water that's in the system. So the amount of the NAPL that's in the system is going to be, instead of being 87, maybe it's 13%. Which is just this length here, right? 13% versus 87% here. And so these anchor points define the behavior. So there are three important anchor points in this. The pressure at which you get invasion of this, which we'll call the entry pressure. So PC0 equals entry pressure. We'll also call it the bubbling pressure sometimes. And the reason we call it the bubbling pressure is because it's the pressure you have to apply to push a bubble of this NAPL through the biggest possible pore throat in the porous medium to get it into the water-saturated porous medium. And so that's this point here. If you apply this pressure, you'll push this bubble into the porous medium. As you increase the pressure, you'll change the saturation by driving out the water, draining out the water, and pushing in the invading fluid, which is the NAPL. As you keep on raising the fluid, you'll get to some point where you can no longer get any more material in it. You're left with this distribution where you have some small amount of water left in the system, surrounded by all this oil, where the water has this monolayer that surrounds the grains, and the oil is present elsewhere. And that's this irreducible saturation of water, which is this point here, which is going to be, we said, a few percent here. And as then you do the converse, as you decrease the pressure of the oil in the system, the oil comes out. It sucks in water spontaneously, it imbibes water, but as you go back to the conditions you started at, you don't end up with the saturation you started at, which was 100% water saturated, but you end up with a small amount of the NAPL left in. It's at the irreducible saturation of the NAPL, and in this particular case that's of the order of 13% and about 87% water. And so that describes the behavior that we've had. And so basically the characteristics that we've described here still allow us to be able to realize that capillary pressure should be proportional to interfacial tension and be inversely proportional to the diameters of the pores that we're trying to push it into. But now by doing this experiment on a sample of porous medium, which clearly has a whole range of these pore diameters, you get a realistic distribution of this the capillary pressure entry pressures as you saturate the largest pore spaces first, and progressively you then saturate the smaller and smaller pore spaces by applying a larger and larger pressure to the system. Okay, so those are capillary pressure versus saturation curves, and so we've tried to go through this. So very, very important. They're kind of a key concept in what we're dealing with. So we talked about the Leverett curves, and so capillary pressure curves in general just look like this and have some form. The Leverett curves are exactly the same curves as those, but instead of plotting versus capillary pressure, we plot them versus this J function, which is proportional to the capillary pressure, but it's also normalized by interfacial tension permeability and porosity. Otherwise it looks the same. And this is very useful because we know that the ordinates of this is 0.3, and we know something about also the magnitudes of this irreducible saturation of water and this irreducible saturation of the non-wetting fluid in terms of the numbers which these are, just by looking at these curves. So that's just one way of plotting them. The other way to look at this is just another way to plot the data, which is interesting. It's just in that it's grown up in a different discipline. So the Leverett curves have grown out of petroleum, and Brooks-Corey curves have grown out of agronomy or soil science. So they're stated in a slightly different way. But let's look at them. So they're saying the same thing. So what are Brooks-Corey curves? Well, they're named for their originators, who I think were at CSU. I can't remember exactly. But the idea is that if you have a capillary pressure curve, where this is the drainage curve, you increase the pressure to get invasion at the bubbling pressure. Once you get invasion and you keep on increasing pressure, you end up going on this trajectory until you get to some irreducible saturation of water. And as you decrease the pressure, you come back on a trajectory that then splits and goes down to the irreducible saturation of the non-wetting fluid. In the case of the Leverett curves, the two fluids were water being invaded by oil to represent oil reservoirs which are already pre-invaded by oil and which you want to pump water in to get the oil out. In the case of Brooks-Corey curves, the media were air in a partially saturated zone where you have fluids. The fluid is water, the liquid is water. So instead of being oil and water as in Leverett, it's air, water, but the behavior is exactly the same in terms of the capillary pressure curves. This is still the saturation of water, and this is still the capillary pressure, which is the difference between the non-wetting fluid and the wetting fluid, where the wetting fluid is water and the other non-wetting fluid is air, which is mainly nitrogen, right? Some oxygen, at least 10% oxygen, I guess, otherwise we'd all be dead, but mainly nitrogen. And so what you could do, in the same way that we normalized the Leverett curves by plotting them in a different way other than using capillary pressure, you could normalize these curves by again plotting them in some other different way. And so the way that Brooks-Corey chose to normalize them was to plot them in terms of capillary pressure divided by the unit weight of the wetting phase. So this would just be 9.8 kilonewtons per meter cubed, unit weight of water. And also in terms of what's referred to as an effective saturation. And the effective saturation is just whatever the saturation is that you would measure in one of these experiments, but relative to the value of the irreducible saturation of water. So in other words, this value here. So this would be the irreducible saturation of water, whatever that percentage is. We saw before it was a few percent or maybe a bit more on the Leverett curves, right? This amount here, and if you look at the Leverett curves, it's this small magnitude here. And so obviously this is a property that's measured from the experiment. You get it from the experiment. And you can use this normalized effective saturation. All it's doing is it's basically taking the saturation relative to the normalized saturation. So in other words, the top part of this, the numerator of this, is equal to this part here. So this would be now basically the range. Well, okay, actually this is, so this value here is 1 minus SW0. This is the denominator on this. So the denominator on this is 1 minus the irreducible saturation, so it's this length here. And the numerator is just measuring the relative distance of the particular saturation that you find yourself at relative to this point here, the irreducible saturation. So this here is equal to saturation of water that you measure minus the irreducible saturation of water. So this effective saturation is nothing other than this length relative to this length. And so you're just kind of changing the scale. So instead of changing the scale, measuring this between 0 saturation and 1, you're measuring it between this saturation and here and scaling things relative to each other. And so if you have a curve where you have all of these points and you know the values of saturations, so you know a whole series of families of saturations of water and capillary pressures, so you have a whole family of these. So for any saturation, you know the capillary pressure. If you know the saturation, you can calculate the effective saturation by just using it in this expression. And if you do that, you can plot it on this curve. And instead of plotting it on a natural scale, it's plotted on a log scale. Both of these are, this is plotted on a log scale. And if you plot it on a log scale, you find out that it actually, instead of having this curvature to it, it actually plots on a nice straight line that has a gradient to it. And you see some examples of this, I think, on this figure here. So this is exactly the idea. This is capillary pressure divided by unit weight. So it's capillary pressure, but you've just divided by a constant, which is the unit weight of water. And you have these curves that define, in this particular case, I can't quite see this. I don't know if you, this is already modified. This is the actual magnitude of saturation of water. And you modify each of these curves to plot them, instead of being in terms of, well, you have this term which is already normalized. You have this saturation of water, and you plot it as, instead of a saturation of water, as a saturation of water minus the irreducible saturation of water divided by 1 minus the irreducible saturation of water, where you measure this in your experiment basically as this point here for this particular curve. Well, for this curve here, whoops, sorry, this would be SW0. And so you can get it for these curves and replot them. And if you plot them instead of as a normal scale in terms of saturation and capillary pressure, but you plot capillary pressure normalized with unit weight on a log scale here, and effective saturation S sub E also on a log scale, then you end up with a whole series of straight lines, where this is now what the curve looks like that we previously looked at over here. And so same data, but it just looks different. And now it has a certain linear slope to it, constant slope to it, straight line. And it also has an intercept where it hits this curve. Actually, I guess these are unit weights, bubbling pressures divided by the unit weights of fluid, right? Because that's what this is. And so the ordinates of this curve are defined by two parameters. The two parameters are the intercept on this axis, where it hits an effective saturation of equal to 1, and the slope of this curve given by the magnitude of this curve here. And so what we've done is we've taken a curve that's not really very easy to characterize because it has a lot of different features to it. It has an intercept, it has some curvature here going up, it's not constant, and it has some curvature going down, which in this case actually we've ignored this imbibition curve. And we've transformed it into a straight line with constant gradient, which is defined by this value lambda, and an intercept, which is the bubbling pressure, actually the bubbling pressure divided by the unit weight, I suppose, where this effective saturation is equal to 1. And so just like if you have a curve which is x and y, then you can define y equals mx plus c. This is the intercept, m, and you can get the gradient of this curve by defining this here. So this lambda value is just the slope of this line, which allows you now to be able to write an expression which describes the effective saturation of this capillary pressure curve as this. basically this curve here. And the effective saturation is equal to the ratio of the capillary pressures to the bubbling pressures to the power lambda. Or actually, I think it's easier to think of it in terms of this, right? So this is exactly what, let's kind of try and draw this slightly differently from what we had before. I'm going to draw it on its side. Okay, so this is P B over gamma log. This is this curve here, so I'm just going this. This is 1. This is lambda. And this is effective saturation. And effective saturation will go from 1 to 0.1 to 10 to the minus 2 to 10 to the minus 3. And so this is the intercept. So this is actually log. So the scale on this is log capillary pressure divided by unit weight of water. This is actually the bubbling pressure divided by the unit weight of water at this particular point. And so if you like, this is the zero intercept. And so if you take this as the curve going through 0, so in other words, x, y, this curve is y equals mx plus c. In this particular case, c is equal to 0 because it goes through the origin. This is the origin, basically in this case on a log scale. This is 10 to the 0, right? This is 10 to the 0. This is 10 to the minus 1. So 0 is the zero intercept. And this is, if you divide these two by each other, at this point here, the capillary pressure is equal to the bubbling pressure. So this term here is also equal to 10 to the 0. It's equal to 1. And so in a log plot, this is log 1 is 0, log 1 is 0, so this point here is 0, 0. And so the curve is just this expression here, and basically this is what it is. So log effective saturation is equal to the slope of this curve times the log of the pressure normalized by the bubbling pressure. And that's all it is. So it's just a different way of being able to plot these curves so that you get some physical, so you have a simple description of this curve. And they always follow these curves. Okay, so what does that mean? What does that actually buy us something? Well, it actually allows us to be able to describe these curves pretty easily. Let's see if I know how to erase. I'm not sure I do know how to erase. Oh, didn't want that. I want to get rid of that. I guess I didn't want to do that. I guess I'm not sure how to get rid of this now, but I guess perhaps I won't worry about it. Oops. Oh, got rid of it. All right, fine. Okay. Okay, lost my train of thought. Okay, what's the significance of these curves? Well, if you think about it, what do these intercepts mean? So if you think about it, these different bubbling pressures here represent something about entry pressures. So we said that capillary pressures should scale with magnitudes of the interfacial tension relative to the pore diameters. So this curve should say something about this. So if in this case the same fluids are being used to invade this, then the only difference between whether you get invasion at this low pressure or invasion at this high pressure, presumably for the same fluid, is because of the pore structure. So presumably in this particular case, the fact that you get invasion happening at a very low fluid pressure is that this must be big. The diameter must be big. And so if you have an open pore, a big open pore, you'll get invasion of the system earlier. And if you have smaller pores, you'll get invasion under a much higher capillary pressure. So immediately by looking at these, and also by looking at these intercepts here, a low capillary pressure means, if you like, big pores, and a high capillary pressure means small pores. So that says something about it. What else is said about this? Well, these have different shapes. This is very flat, and this is relatively steep. So what does that say about the geometries or the distribution of pore sizes you'd expect to have in here? In this particular case, you're pushing fluid in at some pressure to get to this point. As soon as you've invaded a little bit, it invades a ton of the pore space. So this flat part here says that a lot of the pore sizes are about the same diameter, because as soon as it invades a portion of the porous medium, it invades a whole bunch of it as well. And so when this is flat, it means it's relatively uniformly graded, and when it's relatively steep, it means that it's a whole bunch of different pore sizes that you have to invade by applying progressively higher and higher capillary pressures to be able to get into that space. And so that's how it's represented in this form. On the Brooks-Corey chart, the fact that these curves are relatively shallow, so in other words, it's kind of bending its way up here, whereas the one that we looked at, number 2, is this one, which is almost vertical, right? Which means that when the curve is almost vertical, it means once you've invaded the first bit of the pore space under basically the same pressure, you can invade a whole bunch of the pore space in the system. If it's rotating up to the horizontal, then once you've invaded one part of it, you have to do a change in the capillary pressure to be able to invade progressively a larger amount of the pore space in this. And so the characteristics of this, if you like, are also embodied in this behavior. So vertical means that all the same pore sizes. Closer to the horizontal means that it's a distribution of pore shapes. So that's Brooks-Corey that we've defined. Okay. So what else? Where are we in this? So we knew that we could use capillary models to describe what's going on. They're not very useful when you look at real porous media, and we need to resort to these capillary pressure versus saturation curves, which we can measure relatively easily. We can also use normalized versions of these, either as Brooks-Corey or as a Leverett curve. They're really representing the same data. They're just different ways of thinking about or plotting the data to the system. So we know how to be able to use that. The beauty of being able to normalize these things are that we actually have these ordinates, so that if we know what the properties are of our fluid in terms of interfacial tension, and we know something about properties of our medium that we can measure really easily, such as permeability and porosity, we can actually reconstruct these curves. And what these reconstructed curves will tell us, well, they'll tell us something about what the relative saturations are in different parts of our plume. And of course, we might expect those saturations to be different in different regions of our plume, because the capillary pressures that we might have in different regions would be different. And so that's the reason that we're interested in being able to do this. So let's spend a little bit of time talking about some of the subtler behaviors in these capillary pressure versus saturation curves, PC versus saturation curves. One feature which we've already alluded to is drainage and imbibition, and the fact that these paths are different. We've already looked at this on the Leverett curve, and that is, as you're pushing an NAPL into the system, you go on one pathway. As you're reducing the pressures and allowing water to imbibe, you follow the same trajectory for a portion of it, but then you take a new trajectory and you end up at a different location to where you started. You end up here instead of here, with a certain amount of NAPL left in the system. And so the question is, why is that? And well, the reason is that the wetting of surfaces is hysteretic. And the easiest analog I can think of is if you look at think of a bead of water running down an inclined, well, a windshield of a car. And that is, in the part of the windshield that has never seen any water, which is rolling over, the interface angle between the water and the glass is relatively steep. Here it's about 90 degrees. And it's that because it's treading fresh territory, because it's going over a portion of the glass that hasn't been previously wetted. But the portion behind it, which has this tail to it, has already previously had a bead of water sitting on top of it that's moved across, and so it's dragging this remnant tail of water that's across it. So the behavior here is apparently very different from the behavior here, and so this is where it's invading, this is where it's already been invaded, and so you can think of this in terms of the different proportions of this curve. And so we probably don't need to understand anything much more about it other than that, other than the fact that we'll get this hysteretic behavior. And this hysteretic behavior gives these principal features, which I guess is everything that we need to know about capillary pressure versus saturation curves, is encapsulated really in this one figure. So what do we have? This is capillary pressure on this vertical axis. It's not obscured by being a J function or anything else, or being the Brooks-Corey value. It's just a capillary pressure. It's measured in atmospheres. So an atmosphere is what? 1 atmosphere is equal to whatever atmospheric pressure is, which is equal to 0.1 MPa, 100 kilopascals. So that's what this term on this axis is. So this is 100 kilopascals, 200, 300, etc. Doesn't matter. It's for one particular porous medium. So what do we know? We know that this is the entry pressure, CC0, which we've also thought about in terms of the bubbling pressure. Physically, what it means is if you have two grains and you have a bubble of fluid that you're trying to push between them, then the pressure you have to apply here relative to the water pressure here, so I guess this would be PW, this would be PNW. The capillary pressure you have to apply is the difference between the pressures. The capillary pressure you have to apply is the pressure in the bead relative to the water surrounds it to be able to push it through this this neck between two pores. So that's this magnitude here. As you increase the pressure above that, you start to invade, and so at any particular point that you choose, you would have an amount of non-wetting fluid, and you'd have an amount of, I don't want to obscure this by doing this because I clearly don't know how to erase very well, relative to the amount of water. For these two-phase systems, these two have to add up to 100%. So the amount of oil it invades pushes out an equivalent amount of water and leaves the remaining amount of water in the system. As you keep on increasing the pressure, you go up on this drainage curve to drain the water out. It asymptotes to some value, which is the irreducible saturation of water. And this is the amount of water that's left in the system that you can't really get out by any way that involves using a large pressure. You could evaporate it out by heating it up, for instance, but you can't do it in any other way. And that would mean that the amount of the non-wetting fluid, which is present in the system, is equal to this amount. And so you can think of the water saturation varying from 0 to 100%, or the NAPL saturation varying from 0 to 100% in the opposite direction, right? These two axes on the top and bottom are the opposite. And so the non-wetting saturation at this particular case would be about 70%. The water saturation would be about 30%, and if you add the two together, they equal 100%. If you now reduce the capillary pressure to move down here, then you stay in line with this drainage curve proportion, but then you move away from it, and you'd have this separate trajectory which defines the change in saturation as you get down to this point here. This here is the irreducible saturation of the non-wetting fluid, which if you transfer this point up to here, it's something of the order of, what's this? This is I don't know, 15%, probably 13%, say. Don't know if we used 13% before or not. So we have that magnitude. And so that's everything that we've talked about so far. What you could also do is, if you're invading this water-saturated porous medium with the NAPL, if you get up to this point and decide now to reduce the pressure, what you'd do is you'd end up coming down on a different curve. You jump across from the drainage curve to the imbibition curve on one of these scanning curves, as they're called. And as you go across on the scanning curve, then you end up basically back on this imbibition curve. And now if you came down here to this point here, and now you increase the pressure, then you'd go back on another one of these scanning curves. And so there's an infinite number of these scanning curves that will take you from any place on either the imbibition curve going to the drainage curve, or the drainage curve going to the imbibition curve. And so the behavior is intensely nonlinear. It depends on the kind of pathway that you take of saturation and then desaturation. And that's why these graphs are relatively complicated. But if you're looking for the anchor points that matter on this, the anchor points are the entry pressure, the irreducible non-wetting saturation, the irreducible wetting saturation, which is this, and the irreducible non-wetting saturation, which is this point here. And those are the main components. And then in terms of the behavior, drainage, because it's drainage of water; imbibition, because it's spontaneous imbibition of the hydrophilic water onto the grain surfaces; and an infinite family of scanning curves that allow you to go from one to the other. So that's what the real curves look like. We know that from Buckley-Leverett, if you plot this as a curve in terms of this J parameter, hope I'm not belaboring this too much, then the curve, you have a shape for it. This value here is 0.3. I think this value here was something like a few percent. Can't remember. Let's go back just to refresh our memories. Not this. This curve here, right? So this is a few percent, and this is maybe 85%, so 15. And so this is 3%, and maybe this is 85%. And so what you can do is, if you know something about the properties of your system, you could reconstruct this curve, and you can use these ordinates to figure out exactly what the bubbling pressure would be. And so then the next question is, how do you use these in some useful way to be able to figure out exactly what this capillary pressure is? And so the answer is exactly on this slide here. So let's look at what I think is perhaps the easier system of this. So here's the two systems we can now look at. So we're dealing with a static system, and we could think of a porous medium where we have the ground surface here, we have the vadose zone, the water table, and the tension saturated zone sitting above this. Let's not do this one first. Let's do the NAPL and groundwater one. No, actually, let's do this one first in terms of what it means. So, by definition, the water table is the place where the pressure in the water is atmospheric. So if you take the water pressure as atmospheric as gauge pressure of 0, then on a plot of pressure versus depth, this is height, I guess, depth being above this point being negative, and depth below this point being positive. If you look at the fluid pressure that you would see as you go down in the fluid below the water table, it's no different than going down in a swimming pool, where the pressure would increase relative to the depth below the water table multiplied by the unit weight. The fact that it's in a porous medium instead of being in a swimming pool has no bearing so long as it's simply connected. And so you can calculate as you go down through here what the pressure would be at some depth, and it would be this magnitude. Right? So at some depth z, it would be P1. So what happens if instead of going downwards, you start off at this pressure which we know, which is 0, or atmospheric pressure, we go up? Well, we'd expect the pressure to change in exactly the same way as you go up, but this is going to be decreasing. So it'll be decreasing, hopefully not below absolute vacuum, at which it would cavitate, but it's decreasing as you go up in here. So that's why we call this the tension saturated zone, because basically the water is in tension in this here. And what the entry pressure curve tells us is that until you get to a big enough pressure change, basically this capillary pressure here, PC, until you overcome the ability to push now a bubble of water into the pore space, which happens at exactly this point, then it's 100% water saturated. So it's saturated by water up to the point where you can physically push a bubble of water into the largest pore throat that you have, and that happens at this capillary pressure here. As you keep on going up here, the pressure here, of course, would be even more negative than the value it was at this point, obviously from this curve. And so as you go up some extra amount here, so if you go up this height, you get to this point here. If you double this height to here, just from the slope of this curve, you would double the capillary pressure. And so these aren't necessarily directly next to each other, but they would scale in some way. And so at this particular capillary pressure, you'd expect the saturation at this elevation within the vadose zone to be exactly this magnitude here. So you'd expect to have this much water, and you'd expect to have this much of the non-wetting fluid, SNW, which would be the saturation in this particular case of air. And so that's it. So it's nothing more than that. So you can think of the capillary pressure curve. If you're able to figure out exactly what the capillary pressure is at any point within your medium, here you can calculate it with depth below the water table. It's irrelevant in this particular case. And here you can calculate it above the water table. If you know what the capillary pressure is at this point, then immediately you know what the saturation is. Basically, it's 100% water saturated and 0.00001% saturated in air, just because you get this first invasion. If you double the capillary pressure if you go up twice as far, you'll double the capillary pressure. It'll be twice as negative as it was here, and as a result of that, you can calculate the saturation from this point here. So that's fine. So that allows us to be able to see what the saturation would be as you went up through this column in the vadose zone, and it's going to mimic this behavior here. And so that's useful to us. But we can also take this curve, which we know well, and we can flip it. So in other words, if we take it and rotate it around this axis, can't really draw this very well, right? So that's what this is here. So if you take this curve, you keep this axis constant, and you flip it so it's upside down, and then we can use this curve again for a slightly different condition. So the condition here is now we have the surface of our aquifers here. The water table is at the surface, and we want to invade this and it's filled up with water, and we want to invade this with a little tongue of NAPL, which is this green stuff here, which we have in the system. We know that if we can calculate how capillary pressures change with depth, we can relate the capillary pressure to the saturation by using this curve. So again, we have to figure out exactly what the capillary pressure would be as we go down through the system. So we know the water table is atmospheric. We know as we go down from the water table in the water, the pressures will increase just as they did over here. And so the pressure in the water at any depth is equal to the elevation times the unit weight of the water. We also know that if we have a tongue of this NAPL and it's connected, simply connected from the surface all the way down without any breaks, that as we go down through this, then we would also have the same pressure changes within this. So the pressure changes in the NAPL are also the unit weight of the NAPL multiplied by the depth below the surface. So if you can't see that, the pressure change in the non-wetting fluid is also equal to the elevation change, the depth if you like, times the unit weight of the non-wetting fluid. And so the green curve here is the pressure change you'd see as you went down through the NAPL. And so by definition, the capillary pressure is the difference between these two pressures, the water pressure and the NAPL pressure. It's just this magnitude here. And so at any particular depth that we choose, say this depth here, we can always calculate what the difference is in these pressures. And the difference between the pressures is this capillary pressure magnitude here. And if we plot this capillary pressure magnitude on this vertical axis, it won't correspond one-to-one, obviously, in terms of this is a depth and this is a capillary pressure on the vertical axis. But if you know what this capillary pressure is for this depth, you could go to this figure and figure out exactly what's going on. And so let's just think that they correspond here. So let's do half of this amount, which is this part here. So if you go to this depth and you measure this capillary pressure represents this point here, then in theory you wouldn't be able to get the NAPL to move any further if for some reason you had introduced it to this depth. In other words, the tongue went to this depth and stopped, then it wouldn't be going anywhere, right? Because it can't invade. If by some miracle you start off with the tongue so it's deep enough to be at this point here, now the amount of weight, if you like, behind the tip of this tongue is large enough, the pressure at this tongue is large enough to be able to physically push it beyond here, and it can invade. It'll invade, and there'll be some finite saturation of the NAPL, which will be this small amount here, and the rest, of course, will be water, but you've invaded at some very small saturation. If you double that depth down to this point here, then all of a sudden you've doubled the capillary pressure, and the saturation now that you'd have would be this amount of NAPL and this amount of water. And so these saturations refer to kind of the overall saturations if you take a big volume that includes this tongue and also the material around it. So this, obviously within the tongue it's 100% saturated in NAPL and 0 water, and outside the tongue it's 100% water and 0 NAPL. But if you take the aggregate, the REV, the representative elemental volume, and look at it, and then the behavior you have is some aggregate behavior with a certain amount of non-wetting fluid and a certain saturation of wetting fluid. And so now, as you go down in the section, you can also make a prediction of exactly what the saturation would be with capillary pressure, and capillary pressure should be proportional to the depth, just as it was here. So that's the punchline, is that these capillary pressure versus saturation curves also represent the saturation you'd expect to see as you go up or down in the vadose zone, in this particular case, or up and down in terms of the saturated zone, where the two fluids here are an oil and a water, and the two fluids here are an air and a water. So that's the ultimate use of what we've attempted to do. So those are the behaviors that we've looked at so far. I think rather than do the other things, because I haven't quite timed how long this has taken, but I think it's taken a decent amount of time, is that now we're going to stop here. And we've kind of done this. This is taken care of. And I'll leave the discussion of how deep to go through in class just to make sure that we understand these behaviors. So that's what I'm going to leave it as now. So we started off with capillary behavior in tubes. We talked about capillary pressure versus saturation curves and how those could be constructed. We talked about normalizing them in some way, both in terms of this J function, the Leverett function, and also in terms of Brooks-Corey, to be able to put them in some form where we know what these look like. And so if we know what some useful parameters that describe our system, such as the fluid properties and the aquifer properties are, we can calculate whether we would invade the porous medium. And then most laterally, we applied it to be able to see exactly how we could use it in quite a quantitative manner to be able to look at how saturations change in the soil column, both in the vadose zone and the saturated zone for DNAPL. Obviously this has to be denser than water, otherwise it won't. Otherwise this curve here would be underneath this curve, right? But these are obviously for DNAPLs. in this particular case, denser than water, and to have some kind of practical application to figure out how saturation changes with depth. And of course now, if you wanted to remediate this site, and you're doing an inventory of how much NAPL you're taking out of your system, you could calculate what the total amount of NAPL would be in the system if you knew the volume of your aquifer and you knew the saturation, and you'd have some indication of how much material you'd have to process or take out, and also if you did a mass balance of how much you took out over the time that you're remediating the site, you'd be able to tell maybe when you're getting close to having it as a pristine aquifer again. And also the other ramifications, of course, are that since we know that the irreducible saturation, once you come back here, is not going to, of the NAPL is not going to be present at 100% water saturation, you'd know that you're always going to have a certain amount of irreducible saturation of the non-wetting fluid, which will be this amount here, which of course, in a physical sense, will look just like this. And that is that once you've got as much water, the white stuff in this particular case, back into your aquifer, you'll always be left with this funicular saturation of NAPL. And try as you might to pump water through here, you're never going to be able to drag these things through. You have to have some other way of taking care of it. And so that's a very important understanding for us to have behind us. Okay, I will leave it at that, and I will post this to YouTube. Great, thanks.